Hello.
Good evening.
How are you doing?
Good. How are you?
Good, good, good. Just starting the broadcast on the sharing my desktop. Should start in three, two, one. There we go. So
Okay.
this should show you my desktop screen right now.
Yes.
And we will focus on this topic. Uh, there are like two or three big topics left in this. One of them is this recurrent neural networks. The other one is autoencoders. And the last one is reinforcement learning. Those are the three key things that are left. The 17th chapter is not actually a chapter. It's more like a thank you and closing notes and answers and things like that. So that's what we have in our hand. Today we will focus on 14. And that's the plan. But before I begin, I should just ask you about Thanksgiving, which I didn't. I did in the text message, but didn't even talk. So how was it?
Good.
Good, good. And I did not travel. I stayed home, and uh, uh, I don't plan to travel. So I think I have done enough travel. So no traveling for me, I guess, unless I really want to. So I might travel, but I don't know yet.
You seem
I
to keep
have.
pretty busy.
Sorry.
You seem to keep pretty busy.
I try to keep busy because I think this is my area of passion, my area of interest, and so I keep learning, keep doing new things. And in fact, you may have noticed that I sent out an email the other day. Was it today or something like that?
Yeah, recently.
Yeah, yesterday maybe. Yeah. So this what was that email? Registration now open. So I announced that a new program coming up, basically January. That's the plan. And there are 3 or 4 signups already happened, which is crazy.
Wow.
Which is nice. But it is, I think the feedback that you guys provide, which is exactly how anything should work, is the positive feedback that you give is leads to more people interested in joining, and that is just amazing. And I thank all of you for that. And you have done amazing in I think I saw in LinkedIn you wrote about something which I just saw while browsing around. I just ran into your post. That was very nice of you to do that, by the way. Thank you very much.
All right, sure.
And I really appreciate these things. So having said, I should just cut my recording and start all over, because I don't want to capture all this in the recording. So I'm stopping my recording right now. So it will break the video file. And now I will start recording one more time. And this should again project. I think you should already be seeing my screen, I suspect.
I see a cloud.
Yeah, you see the cloud. You see my handwriting now?
Not yet.
Not yet. Okay, so I will now start it one more time. 3, 2, 1, go. Now you should see it. And now you should see my desktop and my handwriting. Do you see it?
Yes.
Okay. Okay. So what we want to basically mention is I have to cover 3 broad topics. One of them is recurrent neural networks. The other one is autoencoders. And the third one, which is reinforcement learning. And that's I think it'll probably take 3 more sessions, including today's. So I think I am thinking of one session for each of these 3 ideas. That should take care of us going through these concepts and understanding how do we apply that in real life. These are the techniques of using deep neural networks in solving a variety of business problems. Today we'll focus on this idea, and that is the idea of recurrent neural networks, which is, I think, described in this chapter number 14, if I remember right. Yes. And I think we kind of started discussing this the other day, but I want to just begin from scratch and begin from fresh on the top of the chapter, which is, I think, just will also help us in a quick recap. And here we begin with that idea. So this idea of recurrent neural networks. Essentially, think of the previous chapter number 13, in which we discussed what I would call convolutional neural networks. And that was focused more on looking at a given image and all the color information in there, so multiple channels, and maybe X-ray and infrared, and multiple channels that we might have for the same image. We'll divide that into pixels, and each of these pixels that we will have, X versus Y, any number of combinations you can see, we'll divide that range into visible patterns. These are called a variety of names people use it for, and so that's the visual cortex, biological front portion of the brain, where it is responsible for immediately detecting what are you looking at. So if I say, for example, I'm looking at this word CNN, I can just quickly look at it and tell that I am looking at the word CNN, no matter how I write it, how bad I write it like this, or whatever other fact, the way the shape of that thing will look like, I can easily and very quickly detect that it is CNN, because our brains are tuned to detect patterns already, and that's the underlying concept of CNN. So this technique of RNN is different in that it actually applies the concepts of what is known as, I would call it a memory cell. I think I briefly discussed this idea of a memory cell. And that memory cell essentially is something that attempts to remember what was the case before. And so what does that really mean from a simple example perspective? If you have a cell that you provided an input, and you provided at time t equal to, say, 0, like right now, and you provided some input, and it will produce some output at that time. But now the time passes, and as time passes, what we want to be able to do is keep track of what the output was and attempt to remember, and use that as an input in addition to the new input. So this will become y0, and this will be x1, this will be 0, this will be 0, at t equal to 1, and this produces another output. Let's call it y1 at t equal to 1. And so this facet of the idea, or the notion of something that you remember from what happened in the past, and feed that as an input into the system to attempt to calculate the next output from the system. And you can extend the same logic continuously like that and produce y2. And you give this y1 as an input, and of course x2 as another input. And so you keep on doing that iteratively on a time basis. So this unit can be anything that you like. It doesn't have to be seconds. It can be any unit of time. And essentially what is happening in this one cell is it attempts to remember what was the output. It has a very short-term memory. So that's the key phrase that you want to remember as we go and discuss. The idea here is that it remembers the state of the output as it receives new input. It knows what the output was previously. And this is the construct, or the building block of the recurrent neural network construct. And the places or business problems where this technique is used are a variety of types. They're definitely not pictures, but anything that changes over time. That will involve something like time series data, like stock prices, for example, or you speak or I speak, or a car moving around on a highway looks around the periphery or circumference of the body of the car to see what else is outside, and then it can decide what to do in terms of adjusting let me be precise in what I'm talking about. So if you have the highway here, and this is a lane, for example, so this is the divider, and there is just 2-lane highway. One goes this way, the other one goes that way, and you have a car going in that direction, this car going that direction, this car, and you have a little turn here coming up. So this car can detect by looking at the patterns and then make appropriate adjustments on the steering wheel. Like, should it bend this way or should it bend that way? that estimation of how much will it bend and which direction should it bend the steering wheel in order for the tires to rotate correctly and follow the track like that. And that's the track we expect it to follow. And so it has to basically keep looking at what else is ahead on the curve, on the road, on both sides of the road, and basically all the sides of the car, all surrounding areas, and keep looking at what is coming ahead and then appropriately make decisions. So that's the idea of what I would call based on time. It receives input. It has to do things in response to what the new input is. So that this is a change in input. The earlier input was like this, like flat, horizontal, or rather I should say vertical line. And then there is a turn. So just for simplification, I'm making it a flat turn, not a curve turn, but a straight turn, just for simplification of our understanding. So there is think of it as a 45-degree turn. Just assume that that's not how natural the roads are, but I'm just saying. So you will have 45-degree sudden turn. And so that detection of that needs to happen at this point in time. It will detect that something changed, and that has to be taken into account. And that previous position of where the car was, how was it moving, which direction was it going, and now this new input, new angle, will also have to be taken into account as it then makes an appropriate educated decision to turn the steering wheel this direction. And by how much? That depends on a variety of factors. For simplification, we'll just go with the angle. And nothing else changes. That's a simplified assumption of the scenario of a car traveling in that direction in a given example. So this is another example of time series data. You have cases where you're translating from many languages that you speak, any input language that you will have as a primary language, and you translate that into, say, English. I'm just saying my example of, I usually do this all the time, because I'm thinking another language and I'm translating myself into English almost every single day. I think it is natural to me because I've been living in this country for 20 years now. But that's how I used to be, at least in the initial days in this country, where I would take some phrase from here and I actually translate it like that. And so this translation basically is another technique where you can apply RNN, or recurrent neural network techniques. These techniques can be made applicable to examples of machine translation of languages. And you see that in many places. You have Google Translate, you have Facebook Translator, your Microsoft Bing Translator, and a bunch of other techniques that you will see. Even in some cases, I have seen Japanese demonstrations of people holding some device in their hand and speaking in one language, and the device will listen to that sentence and immediately translate that into another language and speak out the other language in form of a natural conversation that you may want to have in another country if you travel to. That technology has evolved. And this technology is actually RNN under the hood. And that is just another example. Here, what we are really attempting to do with the idea of what I call attempt to remember, or a memory cell, has a short-term memory as a building block function, and we will understand how we can use this building block to construct a more complex recurrent neural networks of variety of different types. Primarily, there are these two types that are very, very popular these days. In the last 2 or 3 years, they have gone tremendously popular. This LSTM, which is kind of a weird acronym. It is actually short-term memory, but it is long short-term memory. So it's kind of crazy. Is it long or not? So that's the question. But it's just an acronym. It's long short-term memory, and there's another one called GRU. So it's a simplification of the same technique. And so these are the new techniques in the last couple of years that have evolved. We will discuss those things, and we'll have an example application that will actually apply these techniques to our well-known familiar problem we have been dealing with all along, MNIST database. And now that's a picture recognition problem. So typically it is suited for CNN, but we can solve that and identify what picture we are looking at and identify which number does it contain between 0 through 9 using even RNN. So it will just use the same data set to make a prediction of a picture and say that that picture actually belongs to number 3 or something like that. What are that picture that you feed into this network? So you will see an implementation of this RNN technique, and we'll apply this data set, which is not a natural fit. The natural fit is actually a convolutional neural network, which we have seen in the earlier examples. And I think we were able to see a result of about 99%, roughly about 99% accuracy, which is pretty darn good in case of CNN. And you should see something like 98% in RNN with the same data set in an upcoming example that will come soon. So in our next idea is to understand how do we identify this memory cell itself, like I mentioned here, that one that attempts to remember. And I'm in this example that I'm talking about, we are just discussing very simple scalar values. Input goes in here, and then it produces an output, and that output is fed back into the input. Sorry, this thing. It is fed back into the input like this. So this is how it is illustrated in this example here, for example, like this. It's illustrated like this, but this is not exactly how it should be drawn, because it has the idea of time. So here, this input is at 0. This output is at 0. And this output is at also 0. But then this produces the output of 1 when you feed in the input of a previous iteration and the current input. So that representation of time is very difficult to draw in this picture. That's why we have this idea of expanding it, and that thing is called unrolling the network through time. And this is where it actually clearly demonstrates the concept of memory, the concept of travel through time, as to how the network is actually computing various values of output given a certain input, and also remembers the previous output and feeds that as an input to produce another future output. And that's what you see when you draw it like unrolled through time, that it is correctly depicted in a picture, as is shown here, for example. So if you see any of these pictures, let's begin with this one, for example. Here you see that there is this summation or aggregation function of some sorts, some kind of an aggregation function, and this is your ReLU function. If you look at the ReLU picture, which is basically like this, that's the ReLU, a classic ReLU that we have discussed in the past. And this is your aggregation function denoted by a sigma. And these have annotations of time that are not clear in this illustration. And that's why we have to unroll it through time. And so we'll see that unroll as to how it actually shapes up in this picture. So if you look carefully here, what is going on essentially is what we just discussed, is that at a given time, which is 3 times past in history than now. So this is your now time, t-1, t-2, t-3. The input is coming in, and you are feeding the input, and also an output from a previous iteration. So this is y, t-4, that is coming in from here. It is fed into the system from a previous output, if there is any. If there is none, then it is, if it is like beginning right now, then it is 0, or fed some standard constant value. And then that is fed into the system. And then you have new inputs coming in, producing new output, which is then fed back into the system. And this is where the concept of short-term memory arises, is that you're trying to remember what was it before, and now based on that input and also the current input, calculating a new output. And you keep doing that, and you progress in that direction. So this is the idea of unrolling through time. Now imagine this same picture, but now this time we will put, tensors, or actually vectors, in picture. So here is the same representation of the earlier pictures, but this time we are inputting and outputting vectors. That representation is unrolled through time in a picture that shows like this. So we have these internal bubbles or circles that you see here are the same that we have here, except they are shrunk a little bit, and you have unrolling through time happening. And that is how it will eventually keep on predicting what the output y3 would be, and eventually y4 would be, and keep estimating, and based on past inputs that are provided, and past intermediate outputs that are also provided, to compute the next value of the output. A simple example of this application would be a case in which If you have, I think there's a picture here somewhere. Where is the picture for that? Oh, it's probably ahead, but I'll just briefly draw it. The idea is if you have some values here, like that, and you want to predict what would the next value be, we don't know. So you can feed that data. So imagine if you are like 10 data points here. Imagine there are these 10 dots that I made. So 10. So that is number 1, 2, 3, 4, like that, all the way through 10. And I want to predict the 11th item. What I can do is actually apply such a technique of unrolled through time in 10 different time steps to calculate the 11th output, Y11. And that will be the prediction generated by this sequence of cells or memory cells that will attempt to predict the output on step number 11. As we know, and feed it the input of all the way through 1 through 10, you get the output for 11 based on the input that you provide. So it learns from the previous data points and attempts to predict the next. An application of this will be something like if I say, if I say the word bohemian, and I ask you, can you fill up the sentence or the word? What's the next word? And it's very natural for anybody who has seen the recent movies to just fill up the word, instinctively say Rhapsody, right? Similarly, if you say, if you try to create a sentence, people can immediately fill this up with Rhapsody because they have seen the movie. And so you just say Bohemian, they'll automatically fill up the sentence and correctly predict that you probably had this picture of the movie in mind that you probably saw. Same ideas here. If I say something I, and that's an example coming up in the book also, I drink, and then I fill up leave an empty word for somebody else to fill, and they can put anything here, and a logical person will put any object or any word here that will actually be something that is drinkable, whereas illogical output of this value can be iPhone or a pencil or something like that, which is very illogical. Or if I put the value tea or coffee or milk, that is logical. And so we have to then identify whether these words fit into this place or not. And so that's the phrase you can actually use to complete somebody's sentence that people do very naturally. But machines currently can only when you apply these R and N techniques, and you will see them in application in an example coming up soon. So the math underlying here is actually very simple. It is basically a calculation of what we just discussed. If you look at this picture, specifically this picture here, which is what we are attempting to calculate Y3, Y4, like that. And if you try to calculate YT, it is basically W transpose X for the T time, for the current time, and W transpose Y for the previous time, and some offset, or this is the bias term. So it's basically the same linear equation that we have been using all along. So weights multiplied by the input, another set of weights multiplied by the output from a previous run, T minus 1. And this Wx is a weight matrix, Wy is another weight matrix that corresponds to a previous run like this, T minus 1 output. This is also output. And this is your bias term. So it's actually a simple math. And you have the phi here, that outer function, which can be anything like a ReLU function, for example, or just no function at all, meaning equals 1. Phi can be 1 also, meaning you can ignore it. Or phi can be a ReLU function like this. Or you can have tan H function or other functions that we have discussed. So this is an activation function. So phi is the activation function, for example, ReLU. And that's the equation that we are really referring to. You can see it expanded, and this thing actually is explained here, right, in the as described in the book here. Now we'll talk about the concept of the memory, which I think I already discussed. So it is actually a very short-term memory. Like it's just one term. One term as in, it remembers this y0 and feeds in, and that's it. Then it doesn't remember any longer, because now this new thing has to remember and get fed into the output into the next. And so it has a very short-term memory. That's the underlying idea. What we're really trying to talk about is to generate a sequence and being able to predict something in terms of an output that we want to be able to create. So what we want to be able to do is to transform and apply these techniques in 4 distinctly different ways. And I'll describe them to you, the 4 different ways that we can actually put these to use in real life. So one of the ways is when you have a sequence of some sorts and you want to produce another sequence. An example of this would be if I have a data plot of some sorts with 1, 2, 3, 4, all the way through 10 data points, and I want to find out the data points for the 11th, like that. Or I should say, this is, the beginning at 1. This is going to be beginning at 2. So it will be the same shape of the curve. Sorry. Same shape of the curve again here. But now comes the idea where you can actually predict the value for the next data point right here on the 11th data point. It begins with 2. It shifts the whole thing in by 1 step. That's the output sequence. We have an input sequence that you are feeding into, and it has data points of 1 through 10 in that time frame. We are now shifting it forward in time and going from 2 through 11. And thereby we are able to predict a sequence based on a sequence. And this example is illustrated right here. What we are really feeding into is a pattern of x0, x1, x2, x3, x4, and expecting it to produce an output like that, which is very logical in the sense that we have a sequence that we know we are given as an input, and we want to produce an output sequence. So sequence input, sequence output. That's one technique that we can apply to these short-term memory cells, as we just discussed. That's one approach. The other approach is to only focus on the, let me just draw it again. The other approach, so this is like sequence to sequence. The other approach is to sequence to getting some kind of a vector number. So one number that we are interested in, for example, stock price. Stock price. The price of stock of some stock. So for example, let's stock here. So here we have stocks of some company. Let's pick some company here. So that company, we have a stock price, and we want to be able to predict the price of this company tomorrow. So this is the graph for today, and it closed at apparently that number 174.24, and here's the number data point right there, and we want to be able to predict what would be the closing price of this Apple stock tomorrow. And tomorrow, is it working hours? Not, I don't know. Yeah, it is. It's probably operating. So we can see that. But for that, we need to go back a little bit in time. So this is just the daily intraday. If you go back like 3 months, and here you see daily end of the day values, and you can see that the Apple stock has kind of gone down from a top of say 233 or something all the way through to 174. And given this input, what we are really interested in, so at the peak we have 232.07, and then we go down all the way to this number 174, and we want to be able to apply the technique to come up with the price tomorrow. And that you can do simply by ignoring the rest here and just focusing only on the output, because that's what we're really interested in, is the price that we predict that Apple stock will be tomorrow. And that's the concept of making a prediction all the way. And so we will be fed with a sequence of say 3 months of data of a particular ticker, of a ticker symbol in the stock market, and we want to estimate what would the value be of that one data point, which is tomorrow. And this is totally magical, by the way. When it comes to stock price, nobody can predict future. Nobody. Yeah, otherwise there will be people making bunch of money already. So this stock price predictions thing, I don't actually buy into this idea yet. But maybe one day when people start making money on this, making predictions and trading based on purely RNN based predictions, I think there are some people trying it out, but I don't know for sure that are actually successfully done repeatably. They can succeed in maybe one or two cases. Maybe they succeed in some cases in which there is some arbitrage opportunities. Arbitrage, it's a trader word for short-term opportunity of profit. So if you can make money on arbitrage, if you are interested, I can talk more about that. But the idea of predicting stock prices, I cannot really digest. Maybe I don't know. But if I can predict the stock price of something tomorrow, I will be a billionaire today, like right now. It is so easy to do it. We can use a leverage of a call option or something like that, or a put option, and actually beat the market if I know what is going to happen tomorrow. So when it comes to stock price calculations and estimations, I don't actually trust this system, but that's just me being me, nothing else. The concept applies, by the way. The concept actually does hold true in that you can attempt to make a prediction of what the price will be. And that can be a reasonably accurate assumption, but you cannot bet your money on it. That's the challenge that I find it hard when it comes to stock price estimations. However, the concept of taking a string or taking a string of sequence of inputs and getting a vector or one data point at the output that we expect is another way we can actually use this technique. And that is this example here, where we are just ignoring the intermediate outputs. We don't care about what these numbers are when it comes to stock price estimation, because all we really care about is the price tomorrow. And that's Y3 here in this example. And that's your sequence to vector type of estimations. If you want to, you can apply these techniques to that kind of problem sets. The third type of problem set is if you are given a vector, you can generate a sequence. And this is something like, you have some patterns in the past that you have studied and that you have actually trained your models. And now you give it some value to begin its estimations at that point. So begin here, and that's the value I give. And so now the machine learning algorithm, RNN, when you're applying in this context of given a vector, produce an output of a sequence, it will attempt to produce some output. I don't know what it will actually predict based on prior learning of existing data that you might have used as training data. It might produce some sequence of output. And this is not intuitive. So I'll give you some examples where it can actually apply to intuition. And that idea here is when you have, or you may have heard of this thing called computer generated music. Computer generated music. I don't know if you have heard of it or not, but there is such a thing where, if you tell or train the computer what notes constitute melody and what notes or set of notes do not constitute melody, and feed a ton of data to it, and it trains itself, then you give it a beginning point. So here, and it will automatically produce whatever melody that you expect, that you will call it melodious as opposed to cacophony. And so symphony. So if you produce symphony, this combination of certain frequency patterns. And the way I describe, I'm not a musician, so the way I describe this is like this. If you have some frequency and the other octave frequency, let's call it the F. I call it actually F2. That's my mathematical representation. So F2 is basically double F0. That's your do, re, mi, fa, sol, la, ti, do. So this do again is basically 2 times the frequency of original basis. If you begin with some do, then you end up another do, and that second do is actually twice the first do. That's the math. And intermediate re, mi, fa, sol, la, whatever these guys are basically a 2 to the power 1 by 8, 2 to the power 2 by 8, like that. So it keeps on going. You multiply that by that factor all the way to the until you reach 2 to the power 8 by 8, which is basically 2. And that is the multiplication. So that's the mathematical frequency spectrum of any kind of do, re, mi, fa. And I am ignorant about music. I just want to let you know that I don't understand music, but I know the math of music. And so this math, given this math, if you train a bunch of input notes that you call symphony, and also give it a bunch of notes that you call cacophony or not melody, and then the system will learn. And then all you need to do is give it some range of frequencies to operate on as one data point. Like here, take my data point and begin generating a sequence. And based on its prior learning of what is a good music, what is bad music, or rather not music, it will generate some melody. And you may have seen it, but if not, let me just see if I can find it quickly. So let's go to YouTube and see if we can find some machine learning music. And it should pop up, machine learning music generation. And so this idea of yeah, there it is. How to generate music using LSTM neural network in Keras. So that's an example. So you can maybe do a couple of searches, and you will eventually find that it will produce an output that has these are musical things. So I don't understand it, but there is a GitHub repository, and I know I can run it. And it might sound melodious. By the way, this is a composer. It will compose new melody based on LSTM, this LSTM.py. And so that is something, if you're interested in musically inclined, maybe check it out. As a consequence of this, there will probably be a audio file or music file on YouTube somewhere, which should be here. And let's see if music in TensorFlow, maybe that. I don't know what comes up. I think we'll get a symphony based on some input. So you have to give it a frequency band that I will like to play in. I don't know. I don't use the right musical words. That's why I'm at a loss. But you just give it a frequency spectrum of say 20 hertz all the way to 20,000 hertz. And so you say, you know what, pick this data point and begin. So it will start generating some melody here in that band. And if you pick another data point, maybe here, and say, you know, begin some melody here. So it will create some music in that band, in that range, and it will generate a symphony for you. That's the underlying idea. By the way, the output that you will hear on YouTube when you actually run some searches and play some music, it'll not be bad music. It'll be okay music. It's not going to be like, you know, top of the line orchestra or Beethoven or, you know, Mozart. It'll not be anything close to that, but it will not be cacophony. It will be somewhat audible. I mean, you can bear it. You can bear listening to it at least once. That is, I think, the state of the art. But eventually, you will see improvements in that the music generated by a computer based on what people consider musical or melodious versus not melodious. It has trained itself, and it will generate even better music over time. I still don't like the output that I hear, but things are evolving. So you will see improvements happening in this domain. And this domain was, again, this idea, where you give it a input and it generates a sequence. And that's the concept of a vector generating a sequence. And now comes the fourth one, which is a very interesting one, which is actually a combination of the earlier two that we discussed. So we discussed sequence to sequence. We discussed briefly sequence to vector. We discussed vector to sequence. And the fourth one is a logical combination of these two. In that, what we are really trying to generate is, given one sequence, you delay, because there is a time delay in the memory phrase. So you have to complete this process and actually produce a V output or vector output. Use that vector output, and after that delay, use that vector as another input to generate another sequence. So it produces another sequence based on an input sequence, and this technique is typically used in translation. When you're translating from, say, Hindi to English or some language to some other language, you have to actually complete the whole sentence, understand what the meaning of it is, what the semantic is, and what the speaker is trying to communicate. Capture that essence completely before you even generate the output that you expect to produce. That's the concept of translation. You have to look at and listen to the whole sentence or the context of the whole sentence before you attempt to translate, because you might make mistakes otherwise. Unless, you're very likely to make a mistake when you're translating if you don't know the whole context. And that's the fourth technique, which is where it can be applied, which is the idea of sequence to sequence with a delay in between. And so now the implementation of this technique in TensorFlow is very simple. In fact, this technique here is the way you do manually without using TensorFlow. This is a manual implementation. What we're really doing here is unrolling through time. Let's go see what it does. Unrolling through time. So we have 3 inputs, 5 neurons, so 5 of those memory cells. We are defining a placeholder for input data, and only 2 times here. So 2 time steps. So very short network with unrolling through only 2 times. So basically, the network will look something like, you have an input, you give it an input, and you produce an output. You feed that output here, and also give it another input, and you produce an output. That's it. That's the network we are trying to describe here in this. And this is exactly what you will see, which we have seen in earlier pictures. We'll see that implemented, manually done, without using TensorFlow ready-made algorithms. And the implementation goes something like this. You have the X and X0 and X1 inputs, like here, like this guy and this guy, as placeholders defined. These are the 2 time steps that we have unrolled through time. This is 1 time step, another time step, 2 time steps. And then we have our WX, WY, which are weights. And this is the bias term. We are defining them as variables. And then doing a simple matrix multiplication. This is weights multiplied by X input and a bias term. And all of this is passed through a tan-h function in this example. You can use any function that you like as a activation function. You can use tan-h or ReLU, or I think I would recommend use ReLU, not tan-h, but maybe it depends on an example. Like they have chosen tan-h in this example. That's the output produced at the intermediate level here. And then the next idea involves using the output from a previous step as an input. And that's what you will see here. In our example, we are using the output from a previous run. Y0 comes from here. And it's fed into and multiplied with the weights for Y added that with x1, which is this number, and the weights for x multiplied, and then a bias term. And then you have a tan h function at the very outside between this and that on the entirety of the multiplication of the two parts. So weights and biases for x0 and y0 both, x1 and y0 both, x1 and y0 both with weights and biases added, and then tan h function to get the y1 output. And when you invoke this and provide a sample input, you will see how it actually computes the output that you expect to receive from this very, very simple two cells unrolled through time in 2 time steps. So just 1 and 2, that's it. And here is the output that you see coming out from. But as you know that 2 time steps is too little a time. So we need to have multiple time steps to discuss and deal with some meaningful problem. And if you're now looking at a multiple number of different time steps, you can already envision how complex this code can become. This is just for 2 time steps, and you can see that we can simplify all these, and we don't have to write these things ourselves because TensorFlow does it for us. And that's the next example, is to show you how to write this in TensorFlow. And there are 2 ways to do it. One of them is static unrolling through time. And there is another method called dynamic unrolling through time, which is coming up, which is a better approach, not this, because this has another problem, is that it creates copies for every time step. So if you have like 100 steps, then it will create hundreds of copies. And then in back propagation, you're likely to run into out of memory error if you're limited by or constrained by memory on the machines. That is likely to happen. That is one of the reasons why this method is not recommended, but it's there given here. The result is similar, but you need more memory. So when you look at the that's what they're describing here is it's a bit like writing a program without using loops, and you keep writing y0, y1, y2, y3, y50 like that. And so if you have 50 time steps, like here, you will have these many functions written down one after the other without having to write some kind of a loop that will simplify the code that you write. And the number of variables that you're dealing with will blow out of proportion and will likely to run out of memory errors. And that's where the dynamic RNN function comes into play, which deals with only certain number of time steps at a time. It doesn't unroll the whole sequence of time steps that you're interested in. And it basically deals with only the portion that you need to be worrying about. So there is no need to write such a complex descriptive way of writing. It actually gives you a simpler way of writing, as well as complete the function and the calculation of these unrolling through time in multiple time steps without actually taxing your memory. And that implementation is very, very diligent. And so very, very beautifully written right here, actually, if you look at that. So all you do is you provide an X and you say, give me a basic cell and use the dynamic recurrent neural network, and it will give you the outputs that you expect. So it's like simple, really, really simple. It's too simple to not even have to understand what's going on under the hood. That simple. So that's why we have this discussion up front ahead, especially in the manual way of doing things, which is in this example, which describes exactly what is going on under the hood in 2 steps, in 2 time steps. And then we use dynamic RNN, unrolling through time, which does it for us. And then we have the output for that particular kind of computation that we're dealing with. Now, the next idea, which is, if you have a sequence, which is, we don't know the length of the sequence, which is very likely the case. You don't know how long will I speak when I'm saying something, and my sentence will have so many words and so many characters and all that jazz. So if I'm making a sentence and I begin here and I'll go all the way here, you don't know when will I stop. That's a variable length issue. So my input can be variable. And so that is common scenario. When you have a variable situation of an input, you have to specify that. And you can totally do that by specifying the sequence length argument, if you know the length. If you don't know the length, there is another technique that's coming up, which is if you have an unknown length of the input that you can or need to handle, you can, of course, specify that. If you know a sequence length, you call it out like that and use that length because you already know. If you don't know that, you have to have a marker for end of sentence marker of some sorts. So I finish my input, end of stream, end of sequence marker, and that indicates the end of the sequence. So that marker technique is, I think, variable length. So if you have an end of sequence token that tells you that the input has finished, so that you can now proceed with taking the action that you expect to do on the computation that is necessary for your recurrent neural network. And that idea of using an EOS marker is very common. You have that EOS marker is commonly used in almost every file will have an end of file marker, EOF marker. In any file in a computer system, you have an EOF marker at the end of the file, basically indicates that the file is finished. And so you can file length can be anything what it wants to be, and that marker indicates the length of the file marker. So end of the file. Similarly, end of the string or end of the sequence marker. And any output after that, ignore, like usually we expect to do. Now, how do you train recurrent neural networks? This idea essentially is very similar to what we have discussed all along, in that we have to basically apply the same techniques of backpropagation. And the trick essentially involves unrolling through time. So we know that we have this technique of RNN, which expects the output from a previous step, previous time. So that's the underlying concept as to why we need to unroll through time. And when we are unrolling, and after an unroll through time for all the time, what I call steps, 1, 2, 3, 4, 5. Once you draw it out, you can then apply the same technique that we have used all along in any kind of other gradient descent calculations and all the variations corresponding to finding out the gradients as we backpropagate from any other such neural network. You can apply the same techniques provided you unroll through the time for all the times that you are interested in, all the time steps, which can be large. So that is something that, if you have too many time steps, that becomes a very large network. So you have to then figure out techniques of how do you manage that, the so many different number of time steps. And you can apply similar techniques of handling only a portion at a time, and in doing it in batches to finish, and all those techniques that you saw in earlier examples, in earlier cases, will apply here also. But the only trick is to remember that in a recurrent neural network, you have to really unroll and understand these time steps and unroll the whole network back in time, so you can see how the math is going to flow in. And the math is simple. It is y1 equals weight w transpose x, I should say wx transpose x0 plus wy times y0, this is x1, and bias. So this is your previous output, this is your current input that generates the next output, and this is your bias term. That's the math in its vectorized form all along. And you just repeat that same math across in your unroll through time. Next idea here is to see if we can use the same RNN technique like we're discussing, and apply that to solve a problem that we have already solved, MNIST. That is a picture-based problem. So CNN or convolutional neural networks are more appropriate to solving that kind of problems. But since we know that data set, we have it already, we can use that same data set and apply and understand, use it to understand what RNN is and how can we use that data into understanding and running an example of RNN. Now, in case of a recurrent neural network, we want a sequence of some sorts. Whereas in a convolutional neural network, we want an image input of some sorts. So how do we then convert an image into a sequence? That's the idea that we have to, somehow figure out. How do you take an image and make a sequence out of it? So this transition of concept is actually conceptually simple. If you now look at a given picture of a handwritten number in the MNIST database, you will remember and recall that there are 27 by 27 pixels. And so if you now treat each of these sequence of pixels that we have, there are 27 horizontal lines and 27 such bytes of data. If you take a look at each one of these data one at a time, and let's call them 0, 1, 2, 3, and put in 26. Actually, they're not 27, they're 28 pixels. Yeah, so that's why it is 26, 27. That makes it a 27 all the way. So there's a 28 pixel sequence, followed by this 28 pixel sequence, followed by this 28 pixel sequence. Like that, we are basically creating a sequence using an image, a sequence of pixels, which converts the input that we are looking at in terms of byte values corresponding to this pixel, then this, then this, then this, and like that, all the way up to this number. Last one is the 27 picture beginning with 0, total of 28 pixels in one row. That becomes a sequence, and we will use this sequence structure of bytes, sequence of bytes of how many? 28 times 28 is whatever that number is, 7 something. Yeah, well, some number at 28 by 28. That many bytes long is the sequence of pixels that we will now feed into our network. And so that's what our plan is. And we will basically take a image, 28 by 28. And in this example, the plan is to use cells of 150 recurrent neurons. And so there will be x0, x1, x26, x27. There are 28 number of pixels input here, 28. And then the output is fed into a fully connected 10 units of I should say feed forward neural network. Feed forward, plain old neural network, feed forward neural network. That's a plain vanilla neural network that we like we began discussing. The fully connected units, everything connected to everything else. Like, for example, this. Like that. That's a feed forward fully connected neural network. That's this item with 10 units. This is a sequence of 28 items. And we are going to feed it through a cell of 150 neurons and a fully connected network of 10 neurons. This 10 is the idea that we want to actually come up with at the very end. We want to come up with a value somewhere in between 0 and 9, for which we need to know the state of output. And that's why we are trying to use 10 in the feed forward plain neural network here. Is we want to actually make a prediction. Is it 2 or 3 or 1 or 9 or whatever? That prediction has to happen based on the input that we are providing here. and that's a sequence coming into the system. And that will eventually predict what are you looking at from a picture that you feed into. So if you feed in the picture that looks like this, then you can tell that it's a 3. And so this example, I think we should be able to run in our notebook in here. I think the screen sharing apparently stopped for some reason. I'll start it again. It should start in 1, 0, and now. So screen should be sharing again now. And I'm back. Yeah, and I'm back. And so what I was going to do is see if I can bring up my notebook where we have the notebook here. And this should have the example that we can potentially run. And so I want to get to the example. Where is that? MNIST. Let me start running it. So I begin running step number 1, 2, 3. And this is initial setup. Import TensorFlow, basic neural networks, manual recurrent neural networks. Static RNN and then dynamic RNN that we already discussed. And then we will see packing sequence. Where is the example that I was expecting to see? I think it will come. Dynamic RNN. Okay, so I think it's coming. Setting sequence length, training a sequence classifier. And I think there it is. So here is your data that we are looking at. We have 28 steps, 28 number of inputs, 150 neurons in the recurrent neural network, and 10 in the feed forward network as our output. We have a learning rate chosen as 0.1. We are choosing two placeholders, X and Y, as data inputs, X for input. We are using a basic RNN cell. We are defining our logistic softmax function, which is the final function to produce the output. That is this line here, X entropy, which is based on the softmax cross entropy with logits. This is another name to the same idea that we have discussed in the past, which is softmax classification. The idea is that we will have our implementation that we are looking at the final stage. We have an output that will be receiving some probability value for 0, some probability value for 1, some for 2, like that, all the way for 9. And if you feed in the number 3 as an image, then you will see some probability values of 0.1, 0.1, 0.1, 0.85, like that. I think I messed. It cannot be 85. These had to be gone down. So we'll reduce the numbers. So low probabilities here, some are zeros, 0 probabilities for these values. And then the number 3 gets a very high probability. And so these probabilistic distribution that you're looking at is the chance of probability of a particular number being high for the number 3, and 2, 1, 0, and others are low probability. These are non-zero probabilities. By the way, some of them are 0, some of them are not 0, but this one is high. This number indicates 0.85. So that's your way of communicating that the output is a 3. So this has to be transformed into a exact number, because we don't want to know how likely it is a 1. It is 0.05 probability of it being a 1 when you feed this image to it. But we are not really interested in that probabilistic number. You have to transpose that into a deterministic answer that it is 3. That's the answer. So that's what you want to get to, and that's the underlying idea, which is your sparse softmax cross entropy with logits. That function, essentially, we want to reduce this variable. That's your loss function estimation. We want to attempt to reduce that and minimize the entropy. And we will use this Adam optimizer in this example. Let's go find out what that execution will look like. And we have this same Adam optimizer chosen. It will attempt to minimize the loss function and initialize the variable set. And then we'll actually load our examples and go forward with it. So this is a setup of the problem itself right now. We will execute the setup step. So running it, then we will import our data from MNIST dataset. So we'll run that step. And then we will start the training. So this training, it has already run in the past. You can see the output from a previous 100 and so about 97.9% accuracy on a previous runs. But I will go run it again now for us, and we will let it run. This is basically running this training that we will now go and read, but I'll let it start running. So I'm running it now. This number of epochs 100, batch size 150 is currently running, and this will eventually produce an output that you saw already in a previous run. That is what is running right now. But let's go understand what is running here. So what is going on here is we are trying to minimize our loss function, which is basically the same idea. We have 150 RNN neurons as called out here, and we are feeding it an input sequence of 28 pixels and more 28 pixels and more 28 pixels, like that. And it's a feed going into this recurrent neural network. We are passing it through a 10 feed forward network and then applying a softmax classification at the end. And that is what is producing the output that you expect to see. And we are trying to minimize the loss function for the final answer. So that's this reduction. This optimization is what is trying to minimize the loss. Right there. And when you have that training finished, we will then use it to calculate its accuracy. That's the plan. And we'll now execute this. The execution involves loading up data from TensorFlow. This is another way to load the same data set, the MNIST data set from TensorFlow directly, as opposed to scikit-learn. It also has the same data source. It's the same data coming from multiple places. We load it, import the data. You put this in X test, Y test as a test, and you have that ready for testing when it's time to test. So your train accuracy and test accuracy, both accuracy results will be output from these two functions that are evaluating the X batch and X test. So what we are really running here is iterations in 150 batch sizes, 100 epochs, 100 iterations in the number of epochs, and iterating in the range of the MNIST train numerical number of examples divided by batch size. There are 60,000 examples, and our batch size is 150. That is how we are splitting our batch, and then starting to iterate on training a next batch, and then actually running the training session right here. This is where the session training runs. And when the training finishes, then you estimate for every iteration, every epoch. There are hundreds of these, 100 epochs. And so that for every iteration, you will calculate the training accuracy and the testing accuracy and print them out. That's the plan. So let's see what the execution is. And execution is, where is the execution? Hello? No output for me? Didn't I run it? Thought I running it. Okay, run it again. Maybe I didn't run. Okay, run please. Huh. Where is the output? No output. Crazy. Something wrong. I think it works. I have seen it working. I'll show it to you when it works. So let's keep forward. Let's keep forward. It produces basically the output. And the output that you will see in the case of test accuracy is slightly lower than you see in a CNN. These outputs are where they were there in a previous run that you probably saw, but then I ran it again and it disappeared and it's not running apparently currently. And so run? No, it's going forward but not running. Okay, run it one more time from here. From this point onwards, please execute, execute, execute. Nothing. Whatever. We'll get to that. It runs, by the way. There's no issue. I have seen it working. If you get stuck, we'll do it again another time. Output that you see in this example, they produced 98.04 as the test accuracy. The example that I think I saw was 97 point some number, with slightly, yeah, 97, some good numbers, but again, not as good as a CNN would get. But at least you get the idea that you have the concept of converting an image into a sequence and you feeding it into RNN to come up with a non-standard way of using this technique. By the way, this is not standard. You can further improve upon these techniques and even produce slightly better results by doing the usual stuff. Like, what is usual stuff? Those are to initialize with appropriate values to begin with. And this is based on research by this gentleman called He or Ha. This person has come up with a way to initialize the weights and biases at the beginning of the run so that it actually converges better and faster. We train longer, not just 100 epochs, but more. We can add regularization techniques such as dropout, which is basically a very, very drastic method of just ignore 50% of our interim outputs. So whatever we produce, just 50% of cases, we say, you know what, don't care, forget that. And it's a very well-known technique that we have seen in the past called a regularization technique, known as dropout technique. Just ignore half the output, that is half the interim output during training. Not during testing. When you're testing, you don't want to go dropout like this. So dropout needs to happen only during training, and that reduces the risk of overfitting, and it produces slightly better results than what you're seeing here. And so those techniques we can, of course, we haven't used in this example, but you can apply them. Let us see more examples, see if we can make sense of how we can apply this to the thing that I just discussed early on, stock prices, which doesn't make sense to me at all. As to, you know, if I can predict the stock price of something, yeah, I will, you know, be a billionaire, if not at least 100 billion, easy. If I can tell the price of some stock tomorrow with guarantee, like 100% guarantee, that's what I want. But that's the problem, is these predictions are estimations. They are not 100% guaranteed predictions. That's why nobody is suddenly becoming an overnight billionaire. Because if I have the guarantee of 100% predicting stock price based on historical movements, yeah, I'm done. But that's not the case. It is not 100%. It is a prediction. It has a probabilistic estimation, which is definitely not 100. It is less than 100. It is not 100%. That's why you cannot bet money on it. It is likely to be the case. And that's the idea here. So if you look at this picture, it actually attempts to draw the concept. So if you now look at this picture and maybe choose a different color. And if you look at this span of time here, just this span, and that time span in this graph, if you expand it, just this portion, the highlighted portion here, this blue segment, just take that and expand it. That's what you see here. And the dots, the blue dots here, not the stars. There are two types of pictures. There are stars and there are dots. So just focus on the dots, not the star. So there is a star without a dot here. Don't look at that right now. Ignore all the stars. And you see just the dots. And that's your training data, the dots. And you want to actually produce an output shifted by 1. That's the concept of a prediction. So you have a time series data of some sorts. By the way, this function is known. This function is defined as that function. So we already know it. It's a mathematically generated time series. So we know what the prediction will be because we can actually calculate it mathematically. It's a time function. That's the math. So given that math, we try to zoom in on a segment. That segment we have in mind is that segment that I just erased. And what we know about this is that this thing is likely to drop down at that point. And we want to make sure that our algorithm can actually correctly predict that it does go downturn. So there is a downturn, as we know from this math. This math tells us that at that time, this time, whatever that time is here, 15, and that after that time, it will be not a swing up, but a swing down. We know that through math. But what we will do is attempt to make a prediction. And we'll zoom in on this segment here between, say, time of 12, say, for example, 12. This is the 12 time, and this is 15. So between those 3 seconds we have zoomed in here. So between 12 to 15, roughly. And we want to make a prediction. And the prediction is what we want to have here. And that data is a predicted value. And we know from our math here on the left side is that this star is going to be not here, but definitely here, because the math tells us. But we would like to actually estimate that position of this star. Is it here or is it here? And is it going up or is it going to go down? That prediction is what we are attempting to calculate. And that's the concept here, is that we can apply this to stock prices, air temperature, brain waves, God knows what, or just simple math like this to estimate the future. And we know they're feeding it the data, and it is able to actually correctly come up with that value, which corresponds to number 6, as opposed to a number 8, which is not the case here. We know it is going to go down. And for that, we will see if we can fit this function into an RNN and see what output it produces. So to calculate this, we don't have to go do this math, because that's not the idea. The idea is we already know the math. We want to make an understanding of how the recurrent neural network will attempt to predict the future given history. So this is your history on this side. We want to make a prediction on that side and tell whether it is 8 or 6 here or here. That's the point we want to identify, and we can do that by training 100 recurrent neurons, unroll it over 20 time steps, and this is how you would do it. And you will find that the output is actually this, not that. And that's the underlying concept of the network that we are using. The RNN network uses this data set as an input and correctly is able to predict with a good degree, not 100%, that the value is going to dip down, not go up. And you can execute this and find out. Essentially, what we are, where we find this useful in practice is that in practice, we don't have this function at hand. We don't know. But we still want to make a prediction of what the case will be based on historical data. And that's where these techniques come in handy, because they give us a sense of what would that be, because they're able to detect patterns here and here in history. And based on historical patterns, are able to guess with a good, decent degree of confidence, again, not 100%, but a decent level of confidence as to what the value will be. Is it going to go up or down? And that is the estimation. That is where this thing is helpful in examples as we apply to these cases. And these are just examples. There are more. Now there is this this technique called output projection wrapper. Is an optimization technique of solving this a little faster and a little better. And that technique is described here. By the way, that technique, there is a even better technique than that technique. So there is no point why we should go through that, because the other technique is better solution down here. This is not the most efficient solution, although it is easy. This technique of, as described here, the output projection wrapper is the simplest solution to get to the solution or the computation that we want. The technique that is actually performs better is this one, which is coming up. And so we want to again do the same thing, like we are trying to predict the target, which is the idea of time series predictions. And this is where it gets complicated, and things are now going to get complicated, because it is going to get clumsy complicated, I should say. There's no other way to describe it. It says it is trickier, but a more efficient solution. And you will now see the complications of how that complexity is just from its visualization. The concept here is that let's see what the picture is actually trying to communicate, because this is the idea that we need to actually run to implement what we are looking at from an input perspective. And what this thing that we are discussing here goes in as a building block towards a recent innovation known as LTSM, or LSTM, long short-term memory. That technique is a relatively recent, I think 2017 maybe, as late as like a couple of years ago. It's a very fresh technique, and that's what this is going to evolve into in our discussion as we discuss what is that thing. It is wicked complex math, this one, and you will see it coming up. And I think it is important to just understand what the picture is trying to communicate, because what even this book is describing is that the problem with this LSTM is that if you go into details about how the math works, then you will end up not using it. So the better way to use this technique is to just think of LSTM as a simple cell, a memory cell with an output that is also fed into as an input, except that this is your LSTM. So think of it, if you think of it like that, all your discussions up until now will work just fine, except this cell itself is not a basic cell anymore. It is the LSTM cell. The other cell was just STM, very short-term memory cell. This cell has a longer short-term memory. It has a bunch of other things like forget and remember and some other flags to go along to construct what is known as a long short-term memory cell. And we are really trying to build that. The math is wicked complex, but that's not the point. The point is, how do we get to use it? And the nutshell summary is, think of LSTM as just another cell, and all other techniques that we have discussed already apply. So from a usage perspective, think of LSTM as just a cell and use it. It works wonders and is able to produce much better. In fact, using this LSTM, you can create, and there is an exercise here, and it is already done for us, is you can create an English to French translation system on TensorFlow, and it is built in, and you can see that example functional, and that is where this thing is used. So you will see that example coming up. I think that's the real meat of this discussion, is not to go detail in understanding its math, but more of how do we make use of it to solve problems in real life. So let's go see what the building blocks are, at least from a conceptual perspective, to understand where we are heading towards in constructing an LSTM. That's what this discussion is really driving towards. As you will see, it will soon, this is creative recurrent neural networks, and then deep recurrent neural networks, and then comes your LSTM. There it comes. So we'll go back and first of all understand what this illustration is. You have inputs here, x0, x1, and like that. You are creating what is called a reshape and a stack. So the idea behind a sequence is that you take that sequence, which is coming in a time basis, on a time sequence like T0, T1, things are coming to you in a network as an input. These are these inputs coming in here. And what you want to be able to do is stack them. So you collect them and stack them in a fashion in the number of batch size multiplied by how many steps you have. And you create a stack. And you pass them through a regular fully connected neural network. And then you create a sequence again. That's the underlying concept here. You have to stack this and then reshape it again in form of a sequence. The stacking here involves basically converting a time sequence into some kind of a data point, which you can use a fully connected neural network to do further mathematical computations on, and then convert that back into a time series of these outputs given a given batch size. So that's the underlying concept. You will see that applied in LSTM as it comes. You can the research paper behind LSTM. I think there should be a link to that. That if you're interested, you should read that. Let's see if we can find it. LSTM. I think this is it. It does go into, when was it published? don't have a date for it. These guys don't write dates. How crazy. Well, I think it is 2017. And this is also 2017. So it's a fairly recent thing. So new research, basically. And the so my take on LSTM is to not worry too much about the math currently, unless you're really interested, but to use it, and we'll get to that. We'll go forward with this idea. We'll apply this to the concept of discussion into creative RNN, which I think I've briefly discussed in terms of music creation. The idea essentially is you give it a vector and you generate a sequence. And so, or you provide a seed sequence, a short seed sequence, and it creates a longer sequence. So you think of it like this: you start singing, and you leave it for the computer to complete the whole song. Complete the song for me. Complete the song. That's the idea of creative RNN. Now here you can see the sequences seeded with zeros on the left and with an instance on the right. So, seeding with a range. I start singing like this here, and then the rest is filled up, generated by the machine, the RNN network. That's the underlying idea, that you can apply RNN to generate a sequence based on a short seeding sequence that you provide, like here, for example, in this band, and then it will generate the rest for you, because it is able to predict all the future values and is able to then complete your melody for you. And you can see YouTube videos for this when you get a moment. Try searching for creative recurrent neural networks, and you will see some examples. The melody is not melodious, at least to me, but it's not bad. It's not bad. The thing here is the book. The author is kind of funny at times. He's saying that you feed in all the John Lennon albums to a recurrent neural network and see if it can generate the next Imagine song, which is I don't think it happens, but who knows? Eventually it will happen. Eventually computers will generate creative music. Not currently though. It's not happening right now. It's not creative enough. It's okay. It's you can listen to it. Let's put it that way. And so this idea that we have been discussing up until now is not deep, as in not too many layers and layers and layers of neurons in here. We have been basically discussing a neuron. You feed in an input, get an output, and you feed that back, or rather, I should say, this is the time unroll in time, and you feed that, and like that's what we have been discussing. Now we have to extend this idea into a deeper network, and for that, what we really want to do is to expand our discussions in terms of multiple layers. Pretty much like this, like I'm drawing. So this picture is basically this picture. What we are really looking at is, instead of just having one short-term memory cell or long short-term memory cell or short-term memory cell, LSTM or STM or just memory cell of any type, or using only one of them as opposed to many stacked on top of each other. That makes it a deeper recurrent neural network. And of course, you have to unroll this in time. And that's what this picture illustrates. It's deep recurrent neural network, in that it has three levels of depth, 1, 2, and 3. And it has the same idea. You feed in an input vector and you get an output vector. And this is unrolled through time again. And so there are some defaults that have changed that you can pay attention to. But I think this is the one that most people use. So you don't have to worry about the defaults that was changed. There are some default settings that the state is tuple is false. That was the default before that. But don't have to worry, because most people actually use this. And we are also using this one, the later versions of TensorFlow. So now in this example, they're showing you how do you distribute a deep recurrent neural network on multiple GPUs that we have seen. And there is something that I found as a neat trick that I think you can apply when you're using GPUs. So the idea is, in this trick applies to Google Cloud, by the way. Google Cloud gives us $300 of usage for new users. I think you may have it already. So use that. But when you eventually run out of that free money will run out eventually. And so at that time, and you still want a GPU, the best way to accomplish that goal while you are training yourself to use these techniques, when you want to use a GPU, you want to go use what is called a preemptible instance in Google Cloud. And the price of a preemptible instance is about 4.7 times less than a regular instance. And that is something that you should pay attention to. This is a lot of money. So a regular GPU machine on Google Cloud may be for $1 an hour. This will be roughly about 21 cents. That's a nice deal. The only catch is that it is preemptible, which means that basically means this guy, what's his name? The CEO of Google. Yeah, he can take your machine away anytime he feel like, which means the machine will just die on you, like disappear on you, which is fine as long as you're learning. So you can save money like that. A lot of money there, 4.7 times less. And that is something that is recommended as an approach that I would say, if you are run out of this money already, the Google Cloud money that they gave you initially to begin with. So use preemptible instances and start using GPUs, because they're a necessity these days, given that most realistic real life examples will be using we need to have GPU. Otherwise you will see this problem like I ran into here. The thing sometimes doesn't run. So I am going to actually modify the training program itself to not run it on a machine like this, but instead open up a machine in Google Cloud and just run it there. That's my plan going forward. I will have a notebook created in a GPU machine and run it directly in there. That's what I have researched, and I found out that this is the best way to run it. The preemptible instance scenario is a good way to run. It doesn't cost you an arm and a leg, which is what I would actually be doing going forward. So just reminding preemptible VM instances. And this idea is that they always terminate after 24 hours. That's the catch. Compute engine always terminates after 24 hours after they run for 24 hours. Certain actions will reset this 24-hour counter. So that's the catch. This basically means this is similar to the idea that you may have remember if you remember the idea of spot instance in EC2 cloud instance. EC2 cloud, they are machines available for bidding. You can bid for a lower price than a regular machine. Spot instance machines on EC2 cloud is something that you have to go and actually go do a bidding process and then wait for it to allocate and all that. This is doable, but not really ideal for a everyday usage. You just know that your machine will die at some point. You just give them a fixed price. The price is pretty cheap comparative to a full price machine. And let's see the pricing here. A lower, much lower price. So how much lower? Let's see what the pricing is. They don't describe it in the way I described it. Like I said, 4.7 times less. That's my calculation. They don't describe it like that, but that's my estimation. Roughly about that's the pricing difference you will see. It's much cheaper to run it that way. You're going to run it for 3 hours, you pay 60 cents, you're done with running a GPU cluster. So that's the underlying concept. And I will be switching to GPU based machines subsequently, starting January. And so this concept of running a GPU based network essentially is, that you it says don't do it this way. These are bad ways of doing things. So what is the right way? They're describing it as create a wrapper, your own cell wrapper. Or there is an even simpler technique is to use a library function. There's a device wrapper class. And so that device wrapper you can actually use, but this is the implementation of your own cell wrapper if you create your own. And what this does is avoid the problem of allocation of GPU. So you can pin a GPU like this, you would think, but it is a bad idea because it gets ignored. That's where you need to understand that if you're using GPUs, you go write your own cell wrapper like this, or use this specific class that is a contribution in the recurrent neural network section of TensorFlow. And so what that does is it basically simplifies. You can assign your GPU devices 0, 1, 2, however many you have, and you create your device cell wrapper, which wraps all these devices and creates a multi-RNN cell. Basically, this is the idea of using a recurrent neural network. Now, the underlying idea here is multi-RNN, meaning you are now looking at not just one, but a deeper network like this. You can have multiple layers of interim memory cells stacked together to construct a multi-RNN as opposed to a basic RNN cell. That's the nomenclature in the calls to this recurrent neural network library, is to call the multi-RNN cell. And when this idea is illustrating the idea of implementation of a dropout, the same idea that we have discussed in the past. It's just illustrating that as to how do you apply a dropout. It's no different than in the past examples. The underlying idea of dropout is basically you're training a large, very large, deep neural network. There are too many interim outputs. You can afford to ignore half the outputs. So that's the idea here, is to ignore half the outputs. So you train key probabilities of only half of them, and as a consequence, what you will see is that it actually produces somewhat better results. This is counterintuitive, but we have seen that it actually does improve because it generates regularization and reduces overfitting. Having seen that, you will see that you need to remember again is that in case of dropout applications, you need to understand that you apply dropouts only during training. When you're testing, you want to keep this number as 1 during testing. Otherwise, the same idea applies. Is you want to keep probabilities as half of them you want to ignore, half you want to keep, and testing keep as 1. So let's see now some examples. When we have more or rather larger and very, very deep networks with multiple layers and multiple time step sequences unrolled through time, you run into the same problem that you saw in chapter 11 before. You saw chapter 11, I think it goes through a detailed variety of all possible potential gotchas that people run into when dealing with very large networks. And it describes ways to optimize those techniques. And the techniques are right here. So you initialize with the ha initialization. You use ReLU functions. You use batch normalization, gradient clipping, faster optimizers, ADA optimizers, and a bunch of little momentum optimizers. You saw that. You apply that to basically compute the end product a little bit faster and slightly more accurate than ever before. And those techniques you have to apply. The problem with the techniques that we are now dealing with in recurrent neural networks is there is one more complexity, and that is you have to unroll it through time. And this can be a very, very large case of, if you're dealing with large data, string of data, sequences of data with lots of time steps, and that can be a large number of time steps. That is another way to expand our complexity, by the way. And so what we need to understand is that if you just unroll through the whole time sequence, through the entirety of time of your interest, so however many steps are of interest to you in a given example, and if that number is a large number, then this is just another way to make things complex. The way to think of this is conceptually similar to batch creation. So what we can do is potentially, instead of dealing with the entirety of the entire time unroll of all the time steps, we can deal with only a portion at a time, and then the next portion, and then the next portion, and then the next portion, like that. So we can go back propagating in time only in a truncated fashion. That's the idea here, is you go truncated back propagation in time, and that helps us in basically adjusting and digesting the complexity. Otherwise, if you try to deal with the entire time step that you want to handle in one shot, the problem becomes unnecessarily complex. So break it down into simple truncated portions of time steps as you back propagate and deal with only a portion of time at a given time, and then do the calculations, you will succeed. That's the concept here. The underlying these techniques have essentially resulted in this LSTM idea. So practically speaking, almost every single recurrent neural network uses LSTM or the variation of that known as GRU. So we'll first understand what this picture is, which is basically an LSTM cell. So if you look at this LSTM cell, what it does is think of this entire cell as something that gets an input, it produces an output, and it expects an input from the previous time, like previous as in t-1, and expects the current input and produces an output. So if you look at this entire thing as a black box, it's very simple to comprehend because that's what we have been discussing up until now. However, you can actually use it just like that. Just think of LSTM as a simple cell and go ahead and use it. All you need to go invoke is this function call in the TensorFlow contribution library for recurrent neural networks. Basic LSTM cell as opposed to basic cell or basic RNN cell. Instead of that basic RNN cell, you just invoke the basic LSTM cell and every other computation remains the same. It produces better results. After having understand this, there are subtle differences in the design of this LSTM idea. The key differences are actually in terms of handling these two historical inputs, and this is the current input. These are historical outputs, by the way, outputs from previous runs. And this is the longer term, and this is the shorter term memory. Longer term state. I should say longer term state. And this is the short term state. Short term basically means the previous. That's it. Like you produce an output that goes straight into the next step. So in the next cell you will have there, you have another LSTM cell. This output goes straight fed into right there. So it just carries only the short-term state of one state from the other state to the next state. That's the underlying concept behind the H function. It takes care of the short-term state of the LSTM cell. Now let's go see what the actual cell is going under the hood, doing under the hood. So you have a longer term state, and in that state, this is from a previous run, you have to pass it through a forget gate. What is a forget gate doing? It is basically erasing some memory here, and input gate will add new memory here. And so forget gate will remove some old memory. And so that's the underlying idea of forgetting something in the state that you're carrying forward and like that. So you bring from past and send it to the future, and you're making it go pass through a forgetting stage and an input stage that generates new memory, and it retains that and goes forward with it. And that takes care of the long-term memory or long-term state of the cells as it passes through time steps. Now, on the other hand, on the lower side, this is simply an input, which is basically an output from a previous run. Now here, if you look at the four interim outputs, there is an F output, a G output, I and O output. These outputs are the G is the ultimate output we want to actually go and produce to send as an input to the ultimate memory retention from this cell, and also compute the final output for that stage. These F and I and O are essentially the forget gate, the input gate, and the output gate. So this is the main, think of it as the main gate, this G is the main gate where it is able to produce the output that you expect to actually create. So this is the main gate which produces the output of computation based on these and these inputs. The forget gate function produces the items that needs to be forgotten from the long-term state. The input state and the output state are the output generated to control what needs to be memorized. So that's why you have the input function, input gate produces the output that goes to incorporate in the memory that you want to retain on a long-term basis so that you can take it forward in the next time step. And the output gate is simply produces this output that you want to send for the next step or next time step. That discussion itself is convoluted, to say the least. I mean, there's no doubt about it. There are lots of things that are not super clear about why this matters. It is because we have to read and understand the paper that is under the hood behind LSTM, which is a recent publication, as you have seen. Having said, this idea is complex, so there are more further research that has even further simplified this LSTM idea, and that idea is the idea called GRU. Where is that? It should be the very next one, I guess. There is another idea called peephole. Come up with random names. This is where the peephole connection is the idea, which is the GRU cell, which is a simplification of the LSTM cell. So whatever we saw here in this illustration, this has been simplified a little bit and performs equally good, and that is the GRU cell. So GRU is a simplification of this illustration, but performs equally good. That's what we'll now look. But before that, there is this discussion on peephole. And so that peephole discussion essentially is the idea that we have to have a cell look at the longer term state as well. So this idea of long term versus short term. This is the long term and the short term memory of the memory cell, or the short term memory cell. This idea of being able to look at what has been the long term memory in the sequence of time steps is the ability to keep track of what that long term memory is in your interim calculations, is the underlying idea behind this peephole. So if you look, the logic is right here. Actually, it may be a good idea to give a bit more context by letting them peek at the long-term state as well, and that variation to LSTM with extra connections called peephole connections is something that is also available in TensorFlow. Fine, but I don't think this is popular. This is not the most popular technique. This one is, and that is a particularly popular variation is the GRU cell, which is what the next picture is going to be about, and that is called a gated recurrent unit. Gated recurrent unit is a 2014 paper. Also introduced the encoder decoder network we mentioned earlier, which is a sequence to sequence network with a delay, that earlier discussion that we had. And so this GRU unit is a simpler diagram compared to the one that we saw before in LSTM illustration. And here, the concept is slightly simpler. Is you have an input you're producing an output, you're keeping track of the state as you transition through time steps in a recurrent neural network. Inside, we have a fully connected neural network and another fully connected neural network with inputs coming from historical state and the input to that current time t that we have in hand, that at that time t equals this time t. That is what we are feeding in. We are also feeding in the h, and this goes to both these networks. These are feed forward fully connected networks that produces the r output and a z output. Let's see what these two outputs are. And in the output essentially is basically similar functions. So you have the x function with a weighted matrix, an h t minus 1 function with another weighted matrix, and a b as a bias function. So basically pretty similar to what we had early on. That's the z calculations here. Then we have the r calculations, which takes into account, again, very similar, structurally very similar. You can see that the difference in this, what's the difference between these two are only the labels that are different. The label differences are z and an r. It doesn't tell us much about what the underlying math is. I think to understand the math, we have to really go read the paper, not this book. The book doesn't describe the math much. It is mostly focused on using the libraries, not so much in terms of understanding the underlying math. And so I think that the fastest way to produce an output, as opposed to studying math. So studying math is not wrong, but just saying that you can get the output much faster. So the way this book describes is the programmer's way of using machine learning, as opposed to the statisticians or mathematicians' way of using machine learning. So that's a slightly different approach to machine learning as such. The result of this particular GRU technique is that it produces equally good output. At the same time, it is a little less complex to implement, and that is also implemented in TensorFlow as simply as just calling that function. You define the number of neurons you want and get a GRU cell created, and you can use it just like any other cell that we have been discussing all along, and create multiple layers of those, and basically get your cell replaced by a GRU cell, and it performs better. Having seen this is the one that is used amazingly well in natural language processing, and that is something that we can actually try. So this idea of natural language processing is implemented in TensorFlow, and we should try this. A word to vector. So let's see what that thing is. So let's go see there. It takes us to TensorFlow, and there we have a vector representation of words. So the underlying idea here, before we get into this idea, is let me describe it. Suppose we speak a new language. Let's pick some language. I call it language. Some language called L. That's the language. This language has 50,000 words. They happen to be using Roman way of writing. It's just simplification. So Roman script is used, basically ABCD through Z. That's what they use. Same script, but they have a different language. L, it has only 50,000 words. And what we want to be able to do is to represent this idea of these words in some kind of a mathematical form. So we can then say that, you know what, when I say I like pie, again, this is a made up language, but I'm just assuming that that language also writes I like pie like this. And the meaning is also what we have in English. It's the same meaning. I like pie. And so essentially what I'm talking about is this language L is a subset of the English language. So think of it, that's just a simplistic example. English language is a gigantic language. It has many, I don't know how many words. So this is a subset, just for simplification of understanding. So we'll keep using a subset of that language, the English language, but we are limiting ourselves to only these many words, just for the sake of understanding the concept. And so I write this sentence, and I want to communicate this sentence to a computer, so I can pass it through some recurrent neural networks. So it is basically a string. It's a sequence of things happening. Things happen now, things happen a little bit later, and things that happen a little bit even after. Right? I'm saying I like pie, 3 words. I want to communicate these 3 words to the computer, and I have a dictionary of 50,000 words. I can represent this in a variety of different fashions. One of the ways to implement that representation would be what I would call one hot vector, which we already know is what it means. If you have, say, the state of Hawaii. So if I describe this one hot vector in a different fashion, think of the state of Hawaii. It has 4 islands. Actually, there are more, but I'm just saying 4. So 4 islands. We have the Maui, Hawaii, and what, Kauai, and one more. What's it called? Forgetting the name of the island. Oahu. Yeah. So the 4 islands. So let's call them M, H, K, and O. That's simple. So if I want to write these 4 islands and I want to represent them in a computer form, I can use this technique of one hot vectors. One hot vector essentially is a representation where I can write a vector that contains 4 spots. I can fill it up with a 0 or a 1, and I can associate this with M, H, K, O. And so I can then very succinctly describe that I am talking about the big island, the Hawaii island. If I represent like this, then I can be absolutely sure that I'm talking about the Maui island. So what I'm really saying is, only one of these is hot. Others are not. They're 0. They're not hot. One hot. That's a way to represent. That's one of the ways to represent. There are many others. Now, if you apply the same technique to 50,000 words and you want to write this sentence, you can totally do that and create a one hot vector with 50,000 entries. Most of them are zeros. Some of them, or rather, I should say, only one of them is a 1, and then there are zeros, like that. And there are 50,000 of these guys. One of them is a 1, and that corresponds to the word I. That happens to be this number, 369,000, whatever that number is. Yeah, that number. That number stands for the word I. And the word like corresponds to the word 92. Just saying. And pi corresponds to the number 512. So if I want to write I like pi, I will write it like this. I like pi, in form of a representation that goes like this, like a one-hot vector. Now that becomes a very, very sparse representation. Most of the content here is 0. Only the 369,000th item is a 1. Everything else is 0. This 92th or 92nd item is a 1. Everything else is 0. 512th item is a 1. Everything else is a 0. And so that makes it a very sparse way of describing something, like a sentence. So this is not the best way to describe. So what is the right way to describe then? And so the way to deal with this idea is to create a word to vector representation. So what we are really talking about is the idea of embedding, word embeddings. This idea of word embedding essentially means that if you want to say something like I like pie, or I drink something here, pencil, or I drink water, or I drink milk. Now we know that that is a bad sentence, this is a good sentence, this is a good sentence. What I'm really saying is that this representation that I want to have when I'm storing my 50,000 words in my language called L, and I have these many words, I need to store them in a succinct fashion in what I call, what is known as an embedding, is basically a representation of all these words in a data structure known as embedding, which takes into account the distance. Now this is a crazy way of describing it, but just hear me out. Distance between words. So what exactly is distance between words? So the way I would say that is milk is closer to water. Milk is far away from pencil. That's what I mean by distance. Closer to water, far away from pencil. So we have to have in our data structure where we are storing these 50,000 words in what is known as an embedding, is we'll store these words here in data structure, but we'll actually create what is called clusters of words that are closer to each other and put pencil far away from those guys, and thereby creating some semantic meaning in the data structure itself. And that's the underlying idea of an embedding. And we can, in any language, construct such an embedding for every word in that language. Every word in the language. So this is just a subset of that language for the purpose of discussion. And that's the underlying idea behind embedding. Now, once we have that embedding, what we need to actually do is to be able to first of all understand how do we create that embedding. So the way you create a data structure known as embedding for a place to store all the words in a language, you basically begin with allocating a space to store some word and you fill it up randomly. Random. Which means milk will be closer to pencil and all that. So all the wrong things will happen. They're randomly allocated, uniformly random. And then you start training your neural network in terms of feeding it sentences that have meaning to it. So you will feed this sentence, you will feed this sentence, and you will not feed this sentence. And thereby, what the neural network will do is attempt to rearrange your words inside your data structure so that the distance between the words that are closer in meaning will go closer to each other, and those that are farther away from each other will go away from each other. And that's the idea of embedding. So here you can see some projections being made. Like the cat sits on the carpet, the mat, the floor, but not milk. Right? That's the kind of prediction that people can make intuitively. And so that's the kind of idea under the hood behind this example exercise. Is the where did that go? I think I switched my paper. That link has to take us to word to vector. There's a beautiful tutorial, by the way, in TensorFlow called word to vector, and another one is sequence to sequence tutorial. These, I think you should do it yourself later on. But they are actually, by the way, TensorFlow website has an amazing amount of sequence tutorials already provided. Let's go see this one. If I can locate it right, I will try to run it. See if I can locate it correctly. Yeah, I think so. This should run. Where is my notebook? The TensorFlow. Hold on. There is a way to start a notebook here that I'm not able to locate. I think they must have changed something here, because I saw that there is a way to start a notebook in Google based on this specific example set. Once you get comfortable, you can graduate to word to vector.py. Let's see if that example will take us to. I think they changed it. So I will find out if there is a ready-made button to run this tutorial called word to vector model, which is going to help us understand this idea of word embedding, which I just described to you, which is to create a data structure to store words in a language, like this, for example. And that structure will not be one hot, which is very, very sparse. It'll be a embedding to store words in a meaningful fashion. And that is already done for almost all the languages known to mankind, by the way. And so therefore, there is no need to run embedding again, because these embeddings are already available and they're available to download and use. And so that's where you will find that you should not begin by training a recurrent neural network to construct a new embedding, because it is kind of pointless, because it's already done and it's done better than probably you can do on your own. So it's a good idea to reuse an existing word embedding that somebody has done already and provided in open. You can make use of that and build your work to be able to complete sentences like this, or not like this, but like this and like that, on your own, using the embedding that is already available out there in the open. This example that I'm mentioning here actually does that thing using our own machine in that Google Cloud, which I think the tutorial sequence has changed, because the last time I saw there is a button to just start. There should be this button. Is it deploy button? No. I'll identify where that is. But that tutorial is oh, there it is. Is it this? Yes, this is the beginning point. So yeah, you have to follow through this. You have to go through the run code now button right here. And that should take you to collabresearchgoogle.com, which will instantiate a new, so you have to sign in first, I think, and then enter my password, not this, cancel. Enter my password for this account. And then I log in. And now you have to, I think, agree to the license. And then go forward with it. So this should run. But let's see which example it is running. I think we accepted the license. We are connected on the other corner here. And then we get started in importing TensorFlow, loading the mnist data set. Okay, I think I did not import the TensorFlow function, so importing TensorFlow, and then run the mnist data set. That is downloading data set. That's nicely done, by the way. You can see that it is downloading. It is a ready-made notebook, runs in the Google Cloud Colab Research, google.com, and it has successfully downloaded, I suspect. So we can now build which model is running. It is running a different library, by the way, that is built on top of TensorFlow called Keras. So that's it's a different library here, Keras. And we will see if we can generate a model using Keras library. And come on, run it. Yeah, there it is. Is it running? Yes. And then we will train and evaluate the model. So training is running. You can see the evaluation. This should produce a decent result that we expect like before. And you can see what the model essentially is using Adam optimizer like we saw before. It is a loss function, and loss function is used sparse categorical cross entropy. That's a part of your Keras library functions. It is currently running through so many iterations, I think 5 of them, 5 epochs on the fit and evaluate. So we are already seeing some results here. Accuracy is 94, 97, 98.4, 98 point, that's a good one, 98.86, and the last one should be, so basically another way to run examples. I think this is a better way to run examples, and that's the model I'll be switching over, not running in a local machine, because local machines are somewhat unreliable and somewhat incapable of running complex computations, and cloud machines are much better because they have the ability to grab a GPU if needed. And so we will switch that. Here you see 98.05% accuracy, and the this is the test accuracy, 98.05 test accuracy here, the last one, and the train accuracy is 99, which is, I don't care about training accuracy, I care about test accuracy. So that's the example that we run, but we did not see the example that I wanted to see, which was this, the word to vector, which is essentially what will help us train and create an embedding for a set of words in a language of your choice. And that will give us an idea about how do you classify and put close meaning, put the way I should use this is like this: the words with less distance closer to each other, and the words that are farther from each other should be kept away from each other, because that's the idea. Water and milk are closer to each other, but they are far away from pencil. And that's just a way of saying it. The distance is not actually measured in meters, but measured in concept. And so that's how this embedding idea will be visible in an example that I will point out a link for you. This link that you have in the book is not the right one, apparently. The link has shifted to some other location. We have to identify it. But both these tutorials are actually nice. So try it out. Let's go forward. The idea of word embedding. I think I just discussed this, the one hot vector. So the idea of embedding is, as we discussed, is to arrange words in a data structure that is succinct and is able to be used in a sequence of inputs in terms of words that are coming into your training, into a neural network, that you can actually make a prediction based on a set of dictionary words that you already have in your embedding, in your word embedding. Okay, let's see what else we have here. So I think this we already mentioned, is to remember to reuse. So the idea is to reuse our embedding from places that are already available to us. So if you create new embeddings, it is totally okay to do that, but it's a waste of time. So don't. Instead, use embedding that are already available. If you might have done it in the past, there is no reason to do it again. The meaning of water and meaning of the word milk, meaning of the word water is not going to change depending on problems. The meaning of water is water and milk is milk and pencil is pencil. It's not going to change. And therefore, this embedding that you will have for a set of words that you carry and care about is not going to fluctuate from problem to problem to problem. The water will become water and remain water. And so your embedding will stay. It will not probably change too much unless new words come along that will kind of nudge a little bit and adjust the position of a particular word in an embedding given new knowledge. And so it might so happen that you will find that your embedding in a data structure storing words in your dictionary in the language of your choice might change a little bit depending on what new findings or new language patterns emerge, or new data input that the machine learning algorithm might find and train itself on. It might actually evolve itself. So when you are using a existing embedding and you're allowing it to train given new data input, that means your training will be a little bit slower, because you are actually editing your embedding itself given new data. But if you say that, you know what, my embedding is stuck, I am using only these many words and I don't have any new words and don't have any new meaning to an existing word, meaning my embedding is set, don't touch it. In that case, it can be a little bit faster because you're not mucking around with the data itself. And so it can be a little bit faster, but there is a trade-off here. Is you're dealing with an embedding that is frozen, then your algorithm is not smart enough. If you want your algorithm to be smart enough and perform based on new input that might arise, you have to unfreeze this and let this word embedding of your data set of words in the language of your choice be flexible and be editable and modifiable and unfrozen, which makes it a little bit smarter and a little bit slower because you then do deal with the work. So a little bit of trade-off there. And that's useful in case of machine translation algorithms that translate one language to another. And that's the next idea. So here is an idea of a simple machine translation model, English to French. Let's go see the model in the picture, 14, 15. So this model is basically derived on the earlier model we discussed, we discussed 4 patterns. So sequence, you give it a sequence, it produces an immediate sequence right then and there, immediate. So you have x0, x1, like that, it produces y0, y1 immediately. You have a sequence, it generates a vector. You have a vector, it generates a sequence. The 3, and then the last 2 are combined together in form of a sequence that generates a vector that is used to generate a sequence in a delayed fashion. That is what this thing is. So you give it an input sequence. This can be your English language. So I say, I drink milk is the sentence I'm going to say. So the first thing that comes is your x0, then x1, then x2, like that. And of course, you need to pass this through your network. So what you will do is feed that sequence of words that you have, this like I drink milk, and feed it. And this is corresponding to a word embedding at lookup number 72, at lookup number 3335. These are made up lookups, made up 288. And that made up lookup is based on some embedding that you are using in a given example. And that indicates a sentence that you feed into the system that generates an output that we don't care about. But what we care about is an interim value, which is our vector that we really want to worry about and take it forward to another neural network, another recurrent neural network, which is a vector to sequence model. And that vector is fed into a system, which is again looking up for the right choice of words here, for example. I don't know how to pronounce that in French, but that those 4 words apparently are the translation for I drink milk. I don't know how to pronounce this. I cannot read it. I can read it, but I don't want to butcher it. I'm good at butchering, so I don't want to butcher. But it is your target and it is your prediction. And the prediction can be a little bit wrong or different. I don't know if it is wrong or not. Maybe it is wrong. Maybe it is different. But you wanted DU and you got LE. Is that wrong or not? I have no idea. I'm not a French speaker, but maybe it is wrong. Maybe it is different and also correct, but I have no idea. And so that lookup is happening from here on the embedding lookup on the French database. This is your embedding for English. And so it is fed in based on the sentence you have input. It looks up, produces the encoded output in form of a vector that is fed into another network, and that basically produces the output that you expect to receive, which is your prediction, and an end of sentence marker, because you have no idea when it finishes. So you have to pass along a variable input sequence, and then it produces a output that is in French. I think this is implemented. So let's see if we can find it. Translation model number 10. Oh, it's a paper. Yeah. Sequence to sequence learning with neural. Okay. I want to see some implementation, not this. So I will close it. Let's see if we can find it in our notebook here. That notebook is not functioning, by the way. This one did not function for me. Multi-layer RNN time series. Projection wrapper. Creative sequence. Multiple GPUs. Dropout. LSTM. Embeddings. Yeah, this should function. Let us see if we can get this to work. So this is your word to vector tutorial in TensorFlow, creating embeddings. So we fetch the data. Let's see if that works. Fetching. And then fetch and words. No, it is not functional. I think I need to break it. So I'm going to go break this. Close and halt. Refresh. 14. Load. Okay. Let's go all the way to the bottom where we have our word to vector time series. Word to vector. Drop out LSTM embeddings. Okay, run this one. Please run it. And then run that. And then run again. It's not running. No. But I will give up on this notebook. Something is wrong today. It's not functioning in this machine. It is working as such. I mean, apparently working, but not really working. It says it is running for an hour, but that's a lie. So we will shut this one down and maybe get it to work on another location. This is not functional. So I'll get it to work on Google Cloud and get it functional there. That will help us in understanding this English to French is actually beautifully done. But where is it? Where is it? Should be on GitHub. It will not work in GitHub either, but at least go check. Hands-on. And go to that segment. Then go to 14. And there we should find our yeah, it's not implemented. Apparently it's coming soon. It's not done yet. This English to French translation is coming soon. That translator will show up here in 8 and 9, which is I think the exercise in here. So create a English to French translation system. That 8 and 9 are not done yet. That is a part of an example exercises here. We have the translation idea discussed but not actually run. I will see if I can find something functional and show you on Thursday about this. Yeah. So that I think this finishes this chapter. And what I want to now do is stop recording for today, get together on the next time, which is Thursday, on which we will see if we can get this to function, either this one or at least a couple of examples that uses RNN in the exercise sets that we have here. That will give us a good feel of what RNN can do for us, like we saw in our CNN examples. I want to see if we can get RNN to function. Nothing functioned today. So that is something that I will fix. And we'll get together again on Thursday at 4. That's the plan. And on the Thursday, we will discuss this chapter number 15th, which is about autoencoders. And this idea essentially is let's discuss it that day when we get together. So 15 and 16 is what we will plan to cover in the next two sessions, and that should conclude what we are dealing with right now. And I will get these exercises to function correctly on some other machine, if not on this machine that I have locally here. I'll try Google Cloud and get this to function. So with that, I will stop recording now. And what time is it? It's 6:40.
6:40.
Yeah, 6:40. Okay. So I'm stopping the recording function right now.
Okay.
I'll see you Thursday.
Okay. See you Thursday.
Yep.
Have
Bye.
a good week.
You too. Bye-bye.